Okay, let's have a look. So what about something like this? This is a good one to start with. Reminds us about something important. Okay, on Earth, if a scale shows that you weigh 539 newtons, your mass is what? Now, I always want to relate these back to free body diagrams. That's the best way to think about this because you can visualize the forces that are acting. So if a person is standing on a scale, it's a pretty simple free body diagram. What does it look like? There's the person. What are the forces acting on the person?
Gravity.
Okay, so their weight is pushing down, right? What is a person's weight? We could call it F sub g if we wanted to. But what's it? What is that? What is that? What is weight equal to? What is it again? Okay, acceleration times mass. Good. And the acceleration is specifically, in this case, the acceleration of gravity. Yeah. So it's mg, isn't it? Right, so whenever we talk about F sub g, which is a gravitational force, aka a weight, that's always just mg, right? So the downward force is mg. What's another force that's acting? Yeah, the normal force. That's what the scale is providing, isn't it? The scale is providing the force against our shoes that pushes us upward, right? And when you stand on scales, are you usually standing on scales in rockets or in elevators or in roller coasters? No, you're usually standing on a scale probably in your bathroom, right? It's on a stationary floor. So when you're standing on the scale, you are at rest. So your acceleration is clearly zero. Therefore, the net force acting on you is zero, right? So then I've got these two forces that must be equal and opposite there, right? Does that make sense? Okay, so there's my normal force. And so if I wanted to write this, we could look at this in two ways. We could look at this very algebraically, which eventually we will always do. We will write what's called the equations of motion, and we will go from there, right? If we're going to write the equations of motion, they would look like this. All the forces act vertically, don't they? Right? So if we really want to be technical about this, we could say that the net force, and I could even put a y down there, meaning what? What do you suppose the y stands for? They're up and down. Good. I don't really need it because it's pretty much implied here that the force is vertical, right? That would equal what? Well, we look at our free body diagram and we're just going to look at all the positive contributions and the negative contributions. What's the positive contribution? Yeah, normal force, right? Because that's what's pointing up, which is the positive direction. So we'd say normal force minus mg equals net force is always equal to ma, right? By Newton's second law. But what's the acceleration? Zero, right? So this is equal to normal force minus mg equals zero. And so if I solve this thing for normal force, what do I get? Equals mg, right? If I just add mg to the other side. So what if I want to solve for m? I want to find my mass. What do I do to solve for m? Divide by g. Good. So I could also say then that m equals weight, well, normal force, what the scale is reading, right? The scale reading divided by g gives me my mass, as long as I'm at rest, right? Make sense? Okay, so we did this using an equation of motion, but maybe we could jump right to this equation right here directly from our picture, right? Wouldn't you agree that if I know that the acceleration is zero, that these two vectors have to exactly cancel? So doesn't that mean that the magnitude of the normal force must equal the magnitude of the weight? Right, you get that? So we probably could kind of cheat a little bit for now and say, okay, just based on the picture and the fact that I know that the scale is at rest, I could just jump right down to there. what is my mass? Well, if we could plug in the numbers and find out, couldn't we? M is equal to normal force. The scale reading is 539. And the units are newtons, if we want to include them, divided by what's the acceleration of gravity, standard units? 9.80. What are the units? Yeah, meters per second squared. Well, a newton is really the same thing as a kilogram meter per second squared. And so I'm going to end up with kilograms being left over, aren't I? Right. But we could probably just skip the units. As long as we're using standard units, we don't have to include them. And newtons are our standard units for force, right? So then what does that give us? Somebody with your calculator, what's that give us?
55.
So M is approximately what?
55.
55.0?
You know, it's exactly.
Okay. Okay, so I'll just put 0.0 so we know what that's at. So 55.0 kilograms. That's M, right? So isn't that what we were looking for part A? Yeah, your mass is 55 kilograms is what I'd have to input into Moodle. Got to include the units, don't I? Okay. On the moon, G is different. The acceleration of gravity on the moon is only 1.60 meters per second squared. So on the moon, I would have the same free body diagram, only those vectors would be maybe a little bit shorter, right? In fact, they'd be 1/6 as long. But pretend we already shrunk them, right? So everything looks the same, doesn't it? The scale reading would still be normal force on the moon. And so the scale reading would still be M times G, only this time the M is 1.60, right? So I would just have to multiply 1.60 times, wasn't that 55? Times, oops, I got that backwards. My arrows are all backwards. I gotta fix that. That's gonna mess you up. That arrow is supposed to go where? To G, right? And M, make it a different color. That's M. And whatever that product is my weight on the moon as read by the scale. Does that make sense? It's gonna be a lot less, isn't it? Should be. I should weigh a lot less on the moon. What do we get for an answer? What is 1 point, well, we can do that, can't we? So that's gonna be, about, what is that? 80, oh, yeah, 80, 88, yeah, something like that, right? Is it 88.3?
It's 88 exactly.
80 exactly, okay. 88 newtons, be your weight on the moon. That was questions? Does that make sense? Okay. So really, if you thought about this strategically, we had to calculate the mass first, right? Mass is invariant though. Is your mass ever going to change? No. Your mass is based on all the quarks and subatomic particles that make you up. That's never going to change, right? At least not over the course of just this problem, right? And so mass is the same, but the acceleration has decreased of gravity, and so therefore your weight's less. What would your weight be in distant outer space? 0, because there'd be no gravitational acceleration, right? Okay, how about, isn't this just kind of fun? Isn't it interesting that you can do this stuff? I just think it's so cool. I just like even just talking about it. Just up here talking about it, teaching it, I just love it. So, okay, person stands on a scale in a stationary elevator. The scale reads 687 newtons. What would the scale read when the elevator is moving downward at a speed that is decreasing at a rate of 1 meter per second squared? So there's two parts to this problem, aren't there? right? They're different. You gotta kind of picture them in your head. In the first part, what's the elevator doing? It's stationary, right? Okay, so if it's stationary and the elevator and the scale is in the elevator, it's just like it would be in this room, right? So that's the same free body diagram we just drew. So if the normal force that the scale is telling me is 687 newtons, what is my weight? 687, isn't it? Right? Because in part one, and let's kind of label these. Let me go ahead and grab this thing so I can draw. Is it really warm in here?
Yeah.
I don't think that scale is working, or that thermostat is working. Oh, what am I doing? Paste it. Okay, so for part one, which is elevator at rest, this is our free body diagram. Oops. Normal force, mg, right? So mg is equal to normal force, which is 687, right? So therefore, m is equal to normal force over g, 687 over 9.80, which is about what? Somebody, what's 687 divided by 9.8?
70.1.
Say it again?
70.1.
70.1. Okay, now keep the unrounded number in your calculator though, right? Because we don't need that. So that's our mass, approximated, rounded. Now we're going to go to part two. Part two is different. Part two, what is going on with part two? Now let's think about this. If the elevator is moving downward with a speed that is decreasing, so it's doing this, in what direction is the invisible hand acting there? Upward, isn't it? The good old invisible hand from kinematics. Well, the good old invisible hand is actually representing the net force, isn't it? Right? So the net force must be upward, right? Because we've got a positive acceleration. If I'm losing negative velocity, that's the same thing as gaining positive velocity, right? Okay, so this is telling us right here that A equals positive 1.00 meters per second squared, right? So when I draw the free body diagram for part two, I've got the same weight acting. That hasn't changed. I'm still the same person, right? But what must have happened to the normal force if I'm going to have a positive net force? Invisible hand is pushing in the positive direction. Are they balanced this time? They're not, are they? Because the result has to be, if I look at just the net force, I have to have a positive net force vector when I add the two vectors up tip to tail. So what can you tell me about the normal force then? It's got to be bigger than the weight, doesn't it? Okay, so this is our situation, right? And so what is that telling us? What's that equation telling us? Well, this time we can't say that this is equal to this. That's not true, is it? So now we really do have to write this out as an equation. We're essentially just going to write out Newton's second law, right? So we've got our net force is equal to what? How do I add those up? What's the positive contributor? Normal force is pushing upward. That's the scale, isn't it? So we get normal force, what? Minus mg, and that's equal to, what is net force always equal to? MA, right, MA. Okay, so a lot of this stuff we know or can calculate, right? Or have calculated. So let's kind of draw some lines here. So we know the mass. We know the mass. We know the acceleration, right? The acceleration goes right there. Agreed? We know, we're trying to find, this is what we're trying to find, isn't it? Right? And mg, well, we know what m is. I could multiply 70.1 kilograms times 9.80, but we know that just represents weight, doesn't it? We already found weight in part one. Right? In part one, we found that mg is equal to 700 or 687 newtons, right? So I can just treat that mg as that amount right there, right? Everybody see that? And so I can plug everything in except the one thing that I'm trying to find, which is normal force. Isn't that what I'm trying to find? Because it's asking about what would the scale read? Well, the scale is what's pushing me upward, right? Okay, so if we just do a little algebra here, let's solve for normal force. So normal force just equals, if I add mg to both sides, mg, boy, this thing's not writing very well. mg plus ma, let's plug in what we know, that was 687, right? Wasn't it?
70.1.
The mg, the weight was 687, plus m was 70.1. And acceleration was 1.00. So that's equal to what if I just plug that in my calculator? What, 757.1? What should the units be for force? Newtons. Yeah. So that's what the scale's gonna read. Does that make sense? It read 687 when I was at rest. And shouldn't it read more if it's slowing me down as I'm descending? Think about this in the context of something you've done. We've all been in an elevator that's zooming down from the top floor. As it approaches the ground floor, do you feel heavier or lighter? You feel heavier, don't you, as the thing comes to a stop? Are you really getting heavier? No, but you're experiencing a stronger force against the ground, and that's what makes you feel heavier. It's what the book calls apparent weight, and that's a lot of books do. They call it apparent weight because really it's just what the scale reads. Your weight hasn't changed, right? But that's why you feel, what are you really feeling? And this is kind of a deeper question, but what are you really feeling when you're feeling your own weight? Well, you can't feel your own weight, right? That's like saying, this is the sound of one hand clapping. You can't do it. You don't feel your weight. That's the force of gravity acting on you. What you feel is objects that are resisting that force, right? So you stand on the ground, and I have the sensation of weight because the ground pushes back on me. If I'm in free fall, has my weight changed? No, it's the same, right? So when I'm in an elevator and the elevator floor is pushing on me more strongly, I associate that with my weight, right? Because that's always what my weight means, is the return force when I'm standing on the ground. And so it makes you kind of feel heavier, right? Got it? Okay. All right, moving on. Okay, this is a good one. So if a boy exerts a 112 Newton horizontal force as he pulls a 191 Newton sled across a cement sidewalk at constant speed, which everybody does all the time, so this is a valuable thing to know. We want to know what the coefficient of kinetic friction is going to be, right? Okay, so let's draw this free body diagram. It's going to be a little different. Okay, so here's the sled, right? We want to know what's the coefficient of friction. So let's draw all the forces on the sled. Brady, give me one force acting on the sled. Gravity. Okay. So gravity's acting downward. That's mg. And what's the magnitude of gravitational force, aka the weight? 191 newtons. Okay? Need another one. Give me another one. Olivia, what's another force acting on the sled?
This sidewalk.
The sidewalk's pushing up. So what would we call that probably? Normal force, good. So the normal force pushes up, and what's the magnitude of that force? What do you think? Yeah, 191. How come? You're right, how come?
Constant speed.
Okay, because, yeah, and even if it were accelerating horizontally, is it accelerating vertically? No, we're not observing that sled to accelerate into the pavement, right? That'd be a little weird. We're not observing it to spontaneously accelerate vertically into the air either. It's staying in contact with the level ground, right? So we know that those two are equal and opposite. Okay, so now let's look at give me another force. Deshaun, what's another force acting on the sled? Yeah, boy's pulling on it, sure. Okay, so he's pulling probably with a rope or something. So what would we probably call that force? Tension, yeah, good. So it'd be F sub T. Let's say he's pulling it in that direction. Okay, what's going to be the magnitude of the tension force? Maybe. 112. Okay, last force. What's the last one, Sydney? What's the last force going to be? Okay, well now, if that were it, if that were only the only forces acting, what would we observe the sled to do?
All the time.
Ah, it'd be friction, wouldn't it? Yeah, it'd be accelerating in the direction the boy's pulling it, but that's not what's happening. He's pulling it at constant speed, so there must be some other force resisting him, right? And that's friction, isn't it? Okay, so there's the frictional force, and what must its magnitude be? 112. Right, and those are all newtons, okay? So then we want to know what the coefficient of friction is. Okay, well the coefficient of friction, this takes us back to the equation for a frictional force, which we talked about last week, but it's been a little while. It's in your book though. So what is our equation for a kinetic frictional force? Okay, so we get mu sub k, which is the coefficient of kinetic friction. That's nothing that, it's not some magical number that we should know, it's just something in a table, right? That's telling us, that's the experimentally measured sort of slipperiness of the two surfaces rubbing past each other, right? Times, not mass. Normal force, good. Is that starting to make more intuitive sense why that has to be the frictional force equation? It's gonna be the coefficient that's a product of the two materials, or it's a quality of the two materials, right? Times how strongly they're interacting, how strongly they're being pushed together. The stronger they're pushed together, the more friction. The higher the coefficient, the more friction. Okay, so we know that the frictional force is equal to 112 newtons. We know that the normal force is equal to 191 newtons from our free body diagram, right? And so we can solve for mu sub k pretty easily, can't we? If I were just to take my original equation and divide both sides by normal force, wouldn't I just get mu sub k equals frictional force divided by normal force? So that's just equal to, frictional force is 112 newtons, normal force is 191 newtons, so the newtons cancel. What's 112 divided by 191? So there it is. There's our coefficient of kinetic friction. Okay. Make sense? Doesn't that even kind of make sense? If you think about it, the coefficient of kinetic friction is the ratio of the frictional force, right, which is also how hard the tension force, right? Divided by the normal force. So what would a kinetic coefficient of 1 imply?
The amount of energy it takes to pull a thing.
That the amount of force required to pull it at constant speed is exactly equal to, well, the normal force, which would be its weight, if I'm pulling horizontally, right? So that'd be a pretty high coefficient. That'd be something where it would be just as hard to slide as it would be to pick it up, right? That's pretty high coefficient of friction. It's possible, and a lot of books say it's not, but it really is possible to get a coefficient of friction that's bigger than 1. And you just think, I mean, imagine like really soft rubber being pulled on a rough surface. Can you kind of get a sense that it might actually be easier just to pick that thing up and move it than it would be to slide it? It's pretty rare for that to happen, but it could happen. Okay, questions? Good? Is this helping, going through this? Okay, so that's pretty similar. I think I'm going to skip that one for now. We can always come back to it if we really want to. Yeah, what about this one? This is a pretty hard one. Pretty hard one. Okay, so you push a 23 kilogram wooden box horizontally across a floor at a constant speed of 1 meter per second. The coefficient of kinetic friction between the box and the floor is 0.18. So let me ask you this. We could kind of, let me cut and paste this first of all. I don't want to do too much on this one. I want there to be one really zinger on here that you gotta really work on. But I'll help to maybe help you organize your thinking on this. So there's really kind of two different questions being asked here. There's two different situations being described. There's one that says if we push it at constant speed, right? Then there's another one that says, okay, now what happens if you triple the horizontal force you were previously applying, right? What's probably going to happen if I tripled the amount of force I was applying horizontally? Well, I mean, maybe, but initially it was traveling at constant speed, right? With a certain amount of force. So here's a certain amount of force. Now, if I triple the amount of force I'm applying, what would you expect the stapler to do? It'd accelerate, right? Okay. So when the thing is being accelerated, so let's kind of break this up into maybe two different, oops. So here's situation 1 and there's situation 2, right? In situation 2, here's the crate or the wooden box. There's a, would you agree it's got a weight pushing down? You tell me what are the forces? Weight, normal force pushing up. What can you tell me about those? They're equal because I'm pushing horizontally, right? I've got some frictional force that's resisting me, and say I'm pushing it in this direction. This is going to be a longer arrow, isn't it? Right? Everybody agree? Okay. That's my, we'll call that pushing force, F sub P. Okay. What did it look like originally? Well, originally when I'm pushing it at constant speed, it's very similar, isn't it? Might change one thing about this. You tell me what to change, maybe. So that part's still the same. Frictional force. Let's call this one F sub P. If that's F sub P, what should I call this one? Well, what's it tell you if you triple the horizontal force you apply? So how would I probably want to change that one? Yeah, it's going to be 3 FP, isn't it? Right, does that make sense? Okay. Could you figure out what FP is from the first example? You could, couldn't you? You could figure out the magnitudes in this first one. You could put numbers on all these things, couldn't you? Does that make sense? Okay, what about the second one? Which of those numbers are going to change? Just that one, right? So then wouldn't that allow you to calculate an acceleration? Right? Does that make sense? Because if I knew what this number was, let's just hypothetically say it was 100 newtons. It's not, but let's just say it was, right? Let's say that the frictional force was 100 newtons. Then this would have been 100 newtons, right? So that would have been 100 newtons, and that would be 300 newtons, right? So my net force is how much? How much? Maybe two. How much? 200, right? I'd have a net force of 200 newtons, and so I'd end up with an equation like this. Net force equals 200 newtons, right? Equals MA. But I know my mass, right? So I could calculate my acceleration, couldn't I? And if I could calculate my acceleration, doesn't this really just become, kind of devolve to a kinematics problem? If I knew the acceleration, what's my initial speed for part 2? What is it? It's 1, isn't it? Because we want to know how long does it take me if I'm pulling this thing along at 1 meter per second, and all of a sudden I increase the force by a factor of 3. How long, meaning how many seconds does it take for the box to reach a speed of 3 meters per second, right? So wouldn't you agree that for part 2, my initial speed would have been 1 meter per second. My acceleration would be, well, whatever I calculate, right? My final speed is 3, right? 3.0. And I'm just solving for t. No big deal, right? Make sense? Okay? That's all I'm going to give you on that one. That's enough. Okay. Let's see what else we got. Okay, I'm telling you, this is just really a pretty similar one to the ones we talked about, isn't it? So if we know that when the elevator is stationary, that's what the normal force is. So what's my weight? 763. So I could find my mass, couldn't I? Just divide that by G, 9.8. I'd find my mass, right? Okay, the elevator begins to move upward. When it begins to move upward, the scale reads a constant 826 newtons. So what's the net force acting? If the scale read 763 newtons when I was at rest, what's this? The scale when I start to accelerate upwards, right? The scale reads this. So that means that. So what's it going to be? It's accelerating, isn't it? It's accelerating upward. What's the magnitude of the net force? I could draw a free body diagram if I wanted to, right? We've got the downward force, which is 763. That's my weight. Agreed? But this time for part 2, the upward force, the normal force, is what the scale reads. So what's the net force? Well, how would I find it? Just subtract it, right? There's a net force of 37, so that's going to be what, 63 newtons upward? Okay. $63 upward. Okay, so if I know my mass, can't I calculate the acceleration? Because isn't that just equal to ma? And once again, if I know, hang on a second here. Oh yeah, okay, so if I know what a is, all I'm really trying to do is find a final velocity, right? What's my initial velocity? 0, yeah, it started at rest. So it's just kinematics again, right? And you guys are great at kinematics. You have lots of practice with that. Whoops. Okay. Same kind of deal, isn't it? Same thing, right? We can calculate a net force, either up or down. Well, what's it gonna be if the elevator is descending at constant speed and then it slows to a stop as it reaches the bottom floor? Invisible hand's pushing up then, right? It's kinda like our first one. So we're gonna have a net force upward of whatever, the scale's reading minus my weight, right? And I could calculate my mass, couldn't I? Right? Because weight divided by g is my mass. And so I could figure out what the acceleration is again, right? If I knew the acceleration, this is just a kinematics problem. It's no big deal. Snap, snap, you're done. Right? That's it. Kinematics. Nothing. And that's it. That's the whole darn thing right there. Make sense? Okay. So I'm guessing, I had planned to maybe do something new today, but I'm guessing maybe it would be good for you to have a day to work on that and we'll do new stuff later.